So when determining intermolecular forces of attraction, you need to know a couple things, and this worksheet is going to help you work through that process. So I'm going to start with our first example here is nitrogen. So first thing you need to know is you need to know the formula of the compound you're creating and working on for intermolecular forces of attraction. So for nitrogen, you need to remember that nitrogen is one of the big seven. It's a diatomic atom, diatomic molecule. So the formula for nitrogen is N2. And so when we do our have needs analysis to determine the Lewis structure for this, we need to remember we have two nitrogens. All right, so two nitrogens. Each nitrogen has a total of 5 valence electrons. And I know that because I look on the periodic table, and on the periodic table it shows the electron configuration of nitrogen to be 2-5. So just to prove it to you, I'll show you here. We'll zoom in and we'll look at the electron configuration for nitrogen. And we're looking at this right here. Nitrogen's electron configuration is 2-5. The 5, the last number, that is the number of valence electrons we're talking about here. So that's what we need to consider when we're doing our have needs analysis. All right, so back to this. So we have 5 valence electrons. All right, that means we have a grand total of 10 electrons with which to work. 10 valence electrons to work with, okay? When you consider the stable octet, each atom only needs 3 electrons. So therefore, we're only using 6 of the electrons, meaning we have some non-bonding electrons. We have a total of 4 non-bonding electrons. We have 10 electrons total. We're using 6, so we're only going to use 6. That means we're going to have 4 that are left over. So to do this, we're going to start with 2 nitrogen atoms, okay? And there should be 2 symbols for nitrogen to do our Lewis structure. So we're going to do an N. We're going to do another N, okay? We now need our valence electrons. So we're going to use our 6 bonding electrons. Is it this color or is this? I think we'll do that color. 6 bonding electrons. Those right there. Yep. So it says 6, so we have 2 elements, and those 6 electrons must be between those 2 elements. So there are the 6. We have 4 non-bonding electrons. All right. The 4 non-bonding electrons are going to be split evenly between the 2 atoms. 1 there, 2 there, and 2 there. And now when we consider this, each atom independently has a grand total of 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons. Same is true for the other atom. You consider the other nitrogen. The other nitrogen also has 1, 2, 3, 4, 5, 6, 7, 8. They both have their stable octet. They both are satisfied, so we have a correct Lewis structure. Now you need to determine the shape of this atom. Well, there's only 2 atoms in this whole molecule, so the shape of this is going to be linear diatomic. Linear meaning, in a straight line. Diatomic because there's 2 atoms, so it's going to be linear diatomic. All right. Linear diatomic, and now you have to determine whether it's polar or nonpolar. Well, it's completely symmetrical. If you were to consider the electron cloud of each one, the electron cloud, so if we had electron cloud, it would be completely symmetrical, so it would look something like that. All right, that is a symmetrical, assuming that's a symmetrical shape. It's a symmetrical shape. All right. So we have a symmetrical shape, therefore it is a non-polar molecule. And now to determine the major intermolecular force of attraction, you need to go back to the table that I've made for you. And it's this one here. All right. And we're going to consider our different intermolecular forces of attraction. Dipole occurs when we have polar molecules. Hydrogen bonding occurs when we have really polar molecules, but the induced dipole is only when we have nonpolar molecules. It says right there, nonpolar molecules right there. All right, so this atom, nitrogen, diatomic nitrogen, and it gives you an example of nitrogen, that is going to be a induced dipole. We're going to call that a London dispersion force. Let's go back to our problem here. All right, London dispersion force. And so we're just going to write LDF. If you want to write out induced dipole or London dispersion force, whatever works is fine with me. Okay? One of the things you need to be able to remember how to do is the different shapes. And so you have this table at your disposal. So I would encourage you to get that table out because not all of the molecules on this worksheet are simple two-element linear diatomics. So you're going to need to know whether you have a group 14, a group 15, or a group 16 element. And furthermore, you're going to need to know whether you have 4, 3, or 2 things attached to it, and each one of those things influences the shape. I'm going to skip over that. You don't need that. Let's do the next one here. Carbon tetrachloride. This uses our molecular nomenclature. Carbon, meaning there's only one carbon, all right? Tetrachloride means there are 4 of the chlorides. So we're going to carbon tetrachloride. So CCl4 is our formula. We're going to do our have needs analysis. So we're going to have a carbon, and then we're going to have 4 chlorines. 1, 2, 3, 4. 4 chlorines, okay? We now need to consider how many valence electrons we actually have, how many valence electrons each atom actually has. To do this, you're going to have to look at the periodic table again, all right, and look at both carbon and chlorine. And carbon right here shows that it has 2-4, so carbon has 4 valence electrons, all right, the last number. All right, chlorine, its electron configuration is 2-87. It's going to have 7 valence electrons. So carbon has 4 valence electrons with which to work. Chlorine has 7 valence electrons, and those are going to be used for our bonding. Okay, so carbon, I said, has 4. Each chlorine has 7. And now we need to consider. That is a total of 20. Actually, let's count those up. So 7 times 4 is 28 plus 2 plus 4 is 32. So we have 32 electrons total to bond with. However, now we need to consider what we're going to use to bond. Carbon has 4 valence electrons, and it wants a stable octet, so therefore it needs 4 more valence electrons. Each chlorine has 7 valence electrons. It too wants a stable octet, so it's only going to need 1 more electron in each case, so that's a grand total of 8 electrons going to be used in bonding. Well, when now you consider this, you have a whole mess of non-bonding, electrons. The difference there between what you have, which is 32, and what you're going to use, which is 8, and that gives you a 24 as a difference, okay? So what you're going to need to do is you're going to figure out which atom is going to be in the center. Well, carbon needs to have 4 bonds. Each chlorine needs to bond only once. So probably most likely that carbon's going to be in the center. Oop, hang on. Carbon's going to be in the center. I just messed up my pen. Hang on a second. All right, so carbon's going to be in the center. All right, and now we're going to have 4 chlorines around it. So I'm going to put a chlorine over here, chlorine up here, chlorine over here, and chlorine over here. The bonding electrons. It says we have 8 electrons that are going to be used for bonding. So those 8 electrons, all right, these 8 electrons right here, they are going to be distributed among the 4 different points. So we're going to put 2 there, 2 there, 2 there, 2 there for a grand total of 8. All right. We have our non-bonding electrons. Our non-bonding electrons are 24. So those 24 are going to be distributed evenly amongst the other remaining 4. So that's 6 each. And that's what we're going to end up with is our Lewis dot diagram. The shape of this, well, you have carbon, which is a group 14, in the center. It has 4 things attached to it. So let's consider that. Carbon's a group 14. It has 4 things attached to it. So it's going to be tetrahedral. All right? It's tetrahedral. Consider its polarity. You have to consider that we have a tetrahedron. We have a regular tetrahedron. All right? And we're going to have Cl, 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 Cl. It's completely symmetrical, so it's going to be nonpolar. And again, any element any compound that molecule is nonpolar is going to have as its major intermolecular forces are going to be because of induced dipoles due to either London dispersion forces or your van der Waals forces. So continue with the process for each one. You have to go through the different steps, and you should be successful.